My dog is asleep and he's dreaming. I don't know if you heard those sounds, but some strange sounds might suddenly happen in the background. So sorry about that in advance. So I think we can get started. So thank you all for coming today for our next AGN seminar series. And I'm delighted to introduce to you Mar Mezcua. Mar got her bachelor's degree in physics with a specialization in astrophysics from the University of Laguna in Spain. And she then went on to get her PhD at the Max Planck Institute for Radio Astronomy in Bonn, Germany. And then she held postdoc positions at the Canary Islands, then at CFA and the University of Montreal, before returning to Spain, where she is currently a staff scientist at the Institute of Space Sciences in Barcelona. So Mar is truly a multi-wavelength astronomer I respect greatly. She's received highly competitive telescope time on a wide range of ground and space-based observatories, ranging from the radio to the infrared to the optical and the X-ray, which is really impressive. And she's published on a wide range of topics, including intermediate mass black holes, ultraluminous X-ray sources, active galactic nuclei, and many topics within that, radio jets and galaxy mergers. And I met Mar at a conference she organized on supermassive black hole seeds. I don't remember how many years ago that was. It was in Italy. And that's the topic of her talk today. And I have to say it was a really delightful, very well organized conference. And I found it very scientifically stimulating. And this is a topic in which she's done some very nice work, including, finding a potential population of intermediate mass black holes in the Cosmos survey and dwarf galaxies. And she's also done some very interesting work on off-nuclear AGNs detected from manga. She's also done some very nice review articles. I have to say that I've really enjoyed reading, and I recommend taking a look at those. And today she's going to be talking about a potential population of intermediate mass black holes found in deep high redshift surveys. So with that, I will introduce to you Mar.
Thank you so much, Rita. By the way, the conference was in Sexton in 2018, I think, summer 2018.
Oh, okay. Yeah.
And we are organizing another one for this September in San Sebastian in Spain, also about seeds, supermassive black hole seeds and dwarf galaxies. Yeah, I could have advertised it at the end of my presentation. I didn't, so I do it now, okay?
Oh,
Pay
okay.
attention
Then I will email that
another such conference in San Sebastian in Spain. Okay. So thank you very much, really, for the invitation to give this AGN seminar. I'm very glad that this happened, this kind of series, especially during the pandemic. So most of you know what an AGN is, I'm pretty sure, but maybe are not aware of what these seeds of supermassive black holes are, right? So I'll try to give an introduction to the topic, and I'll start by talking about the different black holes we have. On the lower mass regime, we have stellar mass black holes, which have up to 100 solar masses according to stellar evolution models. Then on the other end, we have supermassive black holes of more than 1 million solar masses. And we know there's a gap, a point stability gap, where no black hole should be formed in this region between 140 to 160 solar masses. And then in between the low end and the upper end, we should have a population of intermediate mass black holes with black hole masses of more than 100 solar masses, but less than the mass of supermassive black holes, so less than 1 million. And we think that these intermediate mass black holes should be the seeds from which supermassive black holes form and grow. Now, why is this important? Well, because we know that, or we think we know that most massive galaxies host a supermassive black hole at their center, which when actively accreting, we call AGN, active galactic nuclei. And AGN via winds and feedback are able to regulate the star formation and the growth of the host galaxies. So we think that supermassive black holes and their host galaxies co-evolve, grow in tandem. And this is based mainly on the finding of tight correlations between supermassive black hole mass that we see here on the y-axis and some host galaxy properties, such as the luminosity of the bulge or the stellar velocity dispersion. Actually, this black hole mass stellar velocity dispersion or M sigma correlation is the tightest one. And we see it goes here from more than 10 to the 6 solar masses to up to the 10 to the 10 solar masses. Now, what happens is that we found supermassive black holes, quasars of more than 10 to the 9 solar masses when the universe was very young, less than 1 giga-year. And we can see this here in this review from Rosa Valiante, in which we see that at redshift 6 to 7, we have a population of very powerful quasars. The redshift record holder is this one here at more than 7, redshift 7. And then the largest black hole mass is this other one here of up to 10 to the 10. Now, in 1 giga-year, a stellar mass black hole does not have time to grow and become supermassive. You cannot grow from 100 solar masses or less to 10 to the 9 solar masses in only 1 giga-year. That's why we have to invoke seed intermediate mass black holes of between more than 100 or 10 and up to 10 to the 5 solar masses to explain how these supermassive black holes powering the first quasars formed. From these seed intermediate mass black holes and growing via accretion and mergers, you can make it to 10 to the 9 solar masses in 1 giga-year. Now the question that arises is, how do these seed intermediate mass black holes form? And in this sketch, which comes from a review on intermediate mass black holes that I published in 2017, we can find redshift on the y-axis and black hole mass on the x-axis. And this is the population of supermassive black holes at the nearby universe, but also at high redshift, up to redshift 6 to 7, and black hole masses of 10 to the 9 and up to 10 to the 10 solar masses. Now, the supermassive black holes here could form from these seed black holes formed at very high redshift, more than redshift 10, mainly via 3 mechanisms. One of them is the death of the first generation of very massive stars of population 3 stars. This should yield a population of intermediate mass black holes, seed black holes of around 100 solar masses. Then we can have also mergers in dense stellar clusters. This should yield a population of seed black holes of in between 10 to the 3, of around 10 to the 3 solar masses. And then we can have direct collapse of primordial gas. And this should yield a population of massive seed black holes of around 10 to the 4, 10 to the 5 solar masses. Now, in these cases here, you can have growth via accretion and mergers, and you can become supermassive by redshift 6 to 7, especially in the case of direct collapse black hole. In the case of population 3, it's pretty difficult to go from 100 to 10 to the 9 solar masses, even in the case of super Eddington accretion. Now, what happens is that maybe not all these seed black holes did grow and become supermassive. Those that did not grow should be found in the local universe as leftover intermediate mass black holes with a mass that is similar to that of the seed black holes formed here in the early universe. So as you can imagine, there have been multiple searches for these intermediate mass black holes. The first one started in the Milky Way in the form of globular clusters, but then it moved out to extragalactic intermediate mass black holes in ultraluminous X-ray sources and dwarf galaxies. I'll start first with globular clusters. I'll just show a couple of slides. Why globular clusters? Well, because as I said, one of the possible ways for forming intermediate mass black holes is via runaway collisions in dense stellar clusters. So there have been many searches applying dynamical black hole models to observations of kinematic measurements, also to acceleration of pulsars. And in many cases, we find, and this is a compilation also of my review 2017, black hole masses in agreement with intermediate mass black holes. You can see here we have 10 to the 3 to 10 to the 4 solar masses. And this is one example. This is Omega Cen, a very famous globular cluster, candidate to hosting an intermediate mass black hole of a bit more than 10 to the 4 solar masses. Then there's another very famous case, G1, because this is the only globular cluster which has some possible signatures of accretion in X-rays and radio. And I say possible because while here there seems to be a detection, in later works, these detections were ruled out. Why? Well, because in globular clusters, we have little gas, little dust. So any signatures of accretion are very weak, very low. However, we hope that in the future, with the next generation of radio interferometers, we should be able to detect signatures of accretion from globular clusters, from intermediate mass black holes in globular clusters. And apart from globular clusters, another way to try to find intermediate mass black holes in the Milky Way is by means of wandering black holes. What does this mean? Well, first of all, if we have intermediate mass black holes in globular clusters, we expect these intermediate mass black holes to be ejected due to black hole encounters. And secondly, we can also have intermediate mass black holes in the Milky Way, wandering in the Milky Way, coming from infalling satellite galaxies, dwarf galaxies that had an intermediate mass black hole that merged with the Milky Way and that deposit this intermediate mass black hole in the halo of the Milky Way. So if seed black holes were common in the first dwarf galaxies, which merged to form today's massive galaxies, then we expect a population of relic intermediate mass black holes to be found in the halo of the Milky Way. And these are some initial simulations from 2014, in which we see here the Milky Way stellar halo. In red, we have intermediate mass black holes which are naked, which we don't have a bound cluster of stars around. And in blue, the ones that do have a bound cluster of stars around them. In this case, we see population 3 remnants, and these are relic intermediate mass black holes coming from direct collapse. As you can see, we expect way more intermediate mass black holes in the halo of the Milky Way coming from population 3 stars than from direct collapse, as we can see also here. And this is because forming intermediate mass black holes via direct collapse is thought to be a very uncommon mechanism that requires certain specific conditions, not very common, while population 3 stars were thought to be more abundant, more common in the early universe, and therefore we expect more intermediate mass black holes formed via population 3 stars. More recent simulations by Green et al. Found that a population of around 100 wandering intermediate mass black holes with a bound cluster of stars of more than 500 stars should be present in the halo of the Milky Way and should be detectable with current surveys such as Gaia and DCALS. And this is a model image of one of these overdensities clusters in the halo of the Milky Way. And here you can see it in right ascension and declination. And this is the color magnitude diagram expected of such a cluster, in which we see here how these brighter sources should be detectable by Gaia, while the gray dots correspond to sources that should be detectable with DCALS. Now, these are the simulations. In practice, what happens is that while they found a few stars here covering this color magnitude diagram, most of the stars found in this overdensity are actually foreground or background stars. So they conclude that there are no real candidates for intermediate mass black holes in the halo of the Milky Way. And this is another example that is a work being done by my PhD student, Julen Unzaga, also searching for overdensities in the Milky Way by using pan-star data. And he has found way more stars that we plot here in the color magnitude diagram. This is before correcting for foreground background stars. But after correcting for that, we still see quite a bunch of stars that seem to follow a certain structure. And actually, if we compare this to known globular clusters, such as this one here, in which we see there's a main sequence, there's a turn-off here, an horizontal branch, a red clamp, and we compare this to our candidate or to another source found using the script of my student. This is a known open cluster found by the student. We can see that while for the known cluster, there seem to be a couple of structures here that resemble this known cluster, here the structures are not so clear. So most likely, this is not an all globular cluster such as this one here, which is what we were looking for, but more likely, possibly an open cluster. So this was quite of a summary of intermediate mass black holes being looked for in the Milky Way. And now we'll move to extragalactic intermediate mass black holes. I'll start with ultraluminous X-ray sources, ULXs, which are extragalactic and off-nuclear X-ray sources with an X-ray luminosity above the Eddington limit for a stellar mass black hole. So we are talking about X-ray luminosities of more than 10 to the 39 solar masses for a 10 solar mass, sorry, more than 10 to the 39 X per second for a 10 solar mass black hole. Now, most of these ULXs are most likely stellar mass black holes or neutron stars accreting at super Eddington rates. However, the most luminous ULXs, those with nearly 10 to the 41 or more X per second in X-ray luminosity, are the best candidates to being intermediate mass black holes of in between 100 to 10 to the 5 solar masses accreting at sub-Eddington rates. And one famous case is this one here, HLX1, which you can see here is located off-center of this lenticular galaxy. It's very bright in the X-rays with an X-ray luminosity of 10 to the 42 X per second, so at the limit of being an AGN. And it's also very bright in the radio. It presents transient jet radio emission. We see here the green contours from ATCA. And applying the fundamental plane of black hole accretion, which is a correlation between radio luminosity, X-ray luminosity, and black hole mass, we can estimate a black hole mass for this HLX1 of in between 10 to the 4 to 10 to the 5 solar masses. So the source could be the nucleus of a dwarf galaxy that was stripped in the course of a minor merger with this main massive galaxy. Another nice case that we found in 2015 is this one here. This ULX is not so bright. However, we can see here in pink is the X-ray emission, and here in white I'm showing the BLA contours. It has the extended radio emission east and west of the Chandra position, which would be this one here. And applying BLBI observations, we found that at the position of the Chandra X-ray emission, there's a compact core of around 2 parsecs. And applying the fundamental plane of black hole accretion, the black hole mass for this ULX is also of around 10 to the 4 to 10 to the 5 solar masses. So this is another candidate for being an off-nuclear intermediate mass black hole coming from the nucleus of a dwarf galaxy that was stripped in the course of a minor merger. And a very last and very nice case is this one here. This ULX is actually the dimmest among the three that I'm showing, only 10 to the 40 X per second, but it has a bright optical counterpart from which Kim et al. Derive a stellar mass of nearly 10 to the 8 solar masses. Also, the ULX is very bright in the radio. We can see here in pink the contours from the BLA, and these are BLBI observations in which we are able to resolve the radio emission into two components. Applying the fundamental plane, we get again a mass that is consistent with an intermediate mass black hole. So we conclude that this could be the first case of a multi-component radio jet from an intermediate mass black hole. And because the host galaxy is a Seyfert-2 galaxy that has likely undergone a gas-rich merger, we think that again, this ULX could be hosting the intermediate mass black hole of a dwarf galaxy, whose activity was triggered, whose AGN activity was triggered during a minor merger with the main galaxy. So we have seen individual cases for this, but because these are very interesting sources, which could be, as I said, dwarf galaxies with an intermediate mass black hole merging with more massive galaxies, we wanted to perform a larger search. So what we did with Scott Barrows and Julie Comerford in 2019 was to cross-match the Chandra source catalog with the SDSS catalog, applying two criteria. First of all, we wanted to look for offset X-ray sources. And second, we wanted bright X-ray sources, more than 10 to the 41 ergs per second, so that this could be cataloged as hyperluminous X-ray sources such as HLX1. By doing that, we found more than 100 candidates that you can see here. This is the SDSS optical image. This is pan-stars, and this is also pan-stars with Chandra overplotted. The red cross is the main galaxy, while the cyan circle is the position of the HLX. Many of these cases seem to be merging galaxies. Actually, for almost 50 of these more than 100 HLXs, we have an optical counterpart. So we are investigating HST and also Grand Tecan observations aimed at confirming the presence of a stellar counterpart for these HLXs. So looking for stellar features connecting the primary galaxy with the ULX, and also deriving a merger mass ratio, the mass of the intermediate mass black hole, the volumetric luminosity, properties that allow us to further investigate whether there's any merger-driven triggering of the activity of the intermediate mass black hole, also of any growth of the intermediate mass black hole, which could mean that the primordial seed, the intermediate mass black hole seed from the early universe, has grown significantly. And I'll mention this a bit more later. And the last place where to look for intermediate mass black holes that I'm going to focus on are dwarf galaxies. Why dwarf galaxies? As I said before, we expect to find a population of leftover intermediate mass black holes in the local universe, and with a black hole mass that depends on how seed black holes form here at high redshifts. According to simulation, we can actually predict how seed black holes formed depending on the local properties of this population of leftover intermediate mass black holes. Here we have formation via direct collapse in the early universe, and here formation from POP3 stars. Because as I said before, POP3 stars were thought to be very abundant. If seed black holes formed predominantly from population 3 stars, then we expect to find in today's dwarf galaxies, those with a stellar velocity dispersion below 100 kilometers per second, a very high black hole occupation fraction. So we expect many dwarf galaxies today to have an intermediate mass black hole if this formed from POP3 stars. While in the case of direct collapse, because it's thought to have been a more uncommon mechanism, we expect a lower black hole occupation fraction in today's dwarf galaxies. And an imprint on from these two different formation scenarios can be also seen, according to simulations, in the M sigma correlation. If seed black holes form from POP3 stars, we expect here a population of undermassive black holes with respect to the M sigma, while in the case of direct collapse, we expect a flattening here in the low mass M at around 10 to the 5 to 10 to the 6 solar masses. So this is one reason why we want to look for intermediate mass black holes in dwarf galaxies, but there's also another reason, which is the following. We think, or we thought until very recently, that dwarf galaxies were dominated by supernova feedback. This means that stellar outflows evacuate the gas from the nucleus, expels the gas, stellar outflows expel the gas away and prevent black hole growth, hamper black hole growth. Also, dwarf galaxies have low mass, low metallicity, and by low mass, we apply usually in searches for AGN in dwarf galaxies a cut at 9.5 in logarithmic scale. And dwarf galaxies are thought to not have significantly grown via mergers and accretion with cosmic time. So dwarf galaxies are expected to resemble the first galaxies formed in the early universe, and the black holes that they host to resemble as well the seed black holes formed in the early universe. So that's why there have been many searches for intermediate mass black holes in dwarf galaxies in the form of AGN. Most searches have focused on using optical and infrared emission lines. Most of them using the BPT diagram, which I'm showing you here. We have two ratios, emission line ratios in the x-axis, and another one in the y-axis. And depending on how or where your galaxy falls in this diagram, it will indicate whether the ionization, the source of ionization, comes from an AGN or from star formation. By doing that, hundreds of candidates have been found, a few tens of which have been confirmed via X-ray emission. However, the problem of these optical searches is that we are limited to nearby galaxies, to very low redshifts, and to luminous and pretty massive intermediate mass black holes of 10 to the 4 to 10 to the 6 solar masses with high Eddington ratios. To circumvent these biases, we can do one thing. First of all, most of these searches have been using single fiber spectroscopy, such as the SDSS, in which we have a 3 arc second radius aperture centered here at the center of the galaxy. So which happens is that then if we have strong star formation or strong galaxy light in this galaxy, this can dilute AGN signatures. And also if we have of nuclear AGN, for instance, due to a merger or a switch of AGN, so an AGN which is no longer active, this will be also missed by single fiber spectroscopy observations such as this one. Instead, what we can do is to go for integral field spectroscopy. And here I'll show you a work we did with the MANGA survey, in which we have this field of view of the galaxy covered by more than 100 fibers. So rather than having a single spectrum at the center, we have one spectrum in each of these fibers. By doing that, we found that rather than having only one spectrum that we could use for VPT, we have, as you see, hundreds of spaxels, and in spaxels come from a spectrum of a pixel. So we can have a resolved VPT diagram. So we can plot each spectrum from each pixel in the VPT, and we can see that there are some spaxels that are ionized by star formation, others that are ionized by AGN emission, which we could see here. The spaxels ionized by AGN are located at the center and the others in the outskirts. This is what was expected also from SDSS. This gray square here shows what would be the position coming from the SDSS spectrum. So this is a new source. This is a source already identified as an AGN by SDSS. However, we find other interesting cases, such as this one here, which was classified as a composite object by SDSS. But we see that using MANGA, we have lots of AGN two-liner spaxels here in red, which are off nuclear, not located at the center. So this could be a case of, for instance, a switched off AGN, in which the AGN here at the center is no longer active, and what we see is the light echo of the last burst of ionization from the AGN. Then we found other cases such as this one, in which we see lots of star formation at the center. So either here the AGN is obscured, the galaxy light here is dominated by star formation, we don't see the AGN anymore, or the AGN could be of nuclear and located here. And note that this case is a galaxy that is completely missed by SDSS, being classified as star forming. So in total, as a result of this study, of this search for AGN using MANGA, we found 23 new sources missed by previous SDSS searches. The volumetric luminosity of these sources is very low, less than 10 to the 40 X per second, fainter than any previous searches, also in the radio or the X-rays that we see here in blue. Okay, so we are at very low volumetric luminosities. So using integral field spectroscopy, we have not only found a new sample of AGN dwarf galaxies hidden in previous searches, but also a very faint sample of AGN in dwarf galaxies. One of these 23 new AGN is this one here. It is a very nice case because apart from finding AGN emission, we also see that there's broad line emission in H alpha. So we are able to fit a broad component here. And from the width and the luminosity, we're able to estimate a black hole mass of 10 to the 5 solar masses. So in the range for intermediate mass black holes. So this is actually the first case of a hidden type 1 AGN being discovered by integral field spectroscopy. So this was all in the optical, but another way we can go to higher redshifts and also prevent these biases of very high black hole masses and Eddington ratios is to search for AGN dwarf galaxies in the X-rays. This was done by several people, finding tens of candidates out to redshift 0.6. Now we want to go to even higher redshifts and have complete samples so that we can derive the black hole occupation fraction in dwarf galaxies and infer how seed black holes formed in the early universe. We have to go to deep surveys, such as the Chandra Cosmos Legacy Survey, which has more than 2 square degrees covered by all major observational facilities on Earth and in space. As a result of this multi-wavelength coverage, we can have the SED, the spectral energy distribution, fitted and deriving properties such as the stellar mass, the star formation rate, any other properties we need to draw a sample of dwarf galaxies selected as having a stellar mass of less than 9.5, which is more or less the stellar mass of the LMC. And when looking for X-ray emission of these more than 50,000 dwarf galaxies that we have in Cosmos, what we found is only 40 X-ray detections, only 40 out of more than 50,000 dwarf galaxies. However, these 40 X-ray detections are very bright, even after removing the contribution from X-ray binaries and hot gas to the X-ray emission. We find X-ray luminosities of more than 10 to the 40 X per second. These are the sources located here. This would be the one-to-one correlation corresponding to the X-ray emission coming from X-ray binaries. And in the color bar, you can see the redshift. So we have sources out to redshift 2.4 with black hole masses estimated to be of less than 10 to the 6 solar masses, and with rates of accretion of near to super Eddington. Now, one nice thing that we can do with this sample of X-ray dwarf galaxies is to derive the AGM fraction. And we did that for two stellar mass bins that you see here in pink and blue, from 7 to 9 and 9 to 9.5 in logarithmic scale, finding that the AGM fraction decreases with the stellar mass. This is actually something that was later found also by other works. Now, this decrease of AGM fraction with the stellar mass is actually in agreement with cosmological simulations of seed black holes formed by direct collapse, in which, as you can see here, the black hole occupation fraction, which is not the same as the AGM fraction, decreases with stellar mass. Now we know that the black hole occupation fraction is going to be actually higher than the AGM fraction. Yet these results seem to indicate that seed black holes formed predominantly via direct collapse. Another thing that you can do to look for AGN in dwarf galaxies is to go for radio observations, because actually we know that AGN also in dwarf galaxies also have radio jets. And these are two very famous cases, NGC 4395, which is a galaxy I showed before in the optical, has extended jet radio emission, and this is NGC 404, in which we also see extended emission. However, these are individual cases from which we cannot draw statistical results yet. So many searches have focused on deriving bigger, larger samples of AGN dwarf galaxies from radio observations. This is a work by Amy Rines in 2020, in which she observed more than 100 nearby dwarf galaxies with the BLA, finding 13 sources that were consistent with being radio AGN after removing the contribution from star formation. One of such sources is this one here. We see here the compact radio emission. And I'm showing this one because Nolin et al. Recently studied this source, applied shock models and investigated the BPT diagram, finding that most likely the emission of this source comes from a relatively inefficient accretion flow that is able to photoionize or to excite via shocks the surrounding gas. Now, why is this important? Because this is telling us that AGN radio feedback could also be significant in dwarf galaxies and not only in massive galaxies as we had seen so far. We know that in massive galaxies, radio jets are able to hamper and trigger star formation. So it would be very nice to investigate whether this is also the case in dwarf galaxies by means of larger samples and statistical studies. We did that using again the Cosmos survey, by now focusing on the BLA coverage of the survey rather than the Chandra coverage. Note here that we have a very good sensitivity of 2 microyanskis per beam. And again, after removing the contribution from star formation to the radio emission, we find 35 radio AGN dwarf galaxies that you can see here spread in redshift. And we reach a redshift of 3.4. This is photometric redshift, yet it is a record holder for an AGN in a dwarf galaxy. But the most interesting result of this study is that we find for these radio AGN dwarf galaxies jet powers and efficiencies that are as high as in massive galaxies. A similar result was found more recently by Davis et al. They searched also for AGN in nearby dwarf galaxies, but using the LOFAR survey. They found here 78 sources, also with jet powers very high. So we are finding that AGN feedback might also have a very strong impact on dwarf galaxies, as it happens in massive galaxies, triggering or hampering star formation and maybe affecting black hole growth. And this is another very nice result found by Bradford et al. Here using H1 observations. We can see here in the x-axis the distance from the BPT versus the ratio of H1 mass. And we can see that for galaxies farther away from the star-forming region of the BPT, so as galaxies become AGN, the H1, the amount of gas, decreases. So, and this is for isolated galaxies. So here we are not dealing with mergers or environment effects. So this is telling us that most likely AGN feedback is the one that has destroyed or consumed the cold gas, and this is why we see this decreasing here. Now, all these results are actually in line with the finding of AGN outflows in dwarf galaxies based on asymmetries in the O3 line profile, as you can see here. Now, these AGN outflows can have up to more than 1,000 kilometers per second. So this is remarkable for dwarf galaxies. And the most clear and nice example is that of Genis 220. This was an AGN found several years ago in a dwarf galaxy based on radio and X-ray observation. Recent results by Schut and Rines from, I think it was in February, found that there's a filament connecting this black hole here with a recent site of a star formation. And this filament is well modeled by bipolar outflow. So this is telling us that there's evidence here for AGN triggering star formation. See, this is not negative feedback, but an example of positive feedback in which the AGN is able to trigger the formation of stars. Now, why is this all so relevant? This is the sketch I showed you before, in which we have seed black holes forming in the early universe and growing into quasars that we detect by redshift 6 to 7. As I said, those seeds that did not grow should be found in the local universe as leftover intermediate mass black holes in dwarf galaxies. However, what happens if feedbacks and mergers affect the growth of these seed intermediate mass black holes? Then it could be that an intermediate mass black hole found here of around 10 to the 5 solar masses is not the relic of a direct collapse black hole, but is instead a population 3 black hole that has grown significantly from 10 to the 2 to 10 to the 5 solar masses. So if black hole growth is not hampered by supernova feedback, as we were so far assuming, but enhanced by mergers or AGN feedback, then local intermediate mass black holes in dwarf galaxies should not be treated as the relics of the early universe seed black holes. So the question that arises now is then, how can we know whether local dwarf galaxies hosting AGN host the relics of the early universe seed black holes? There are two things we can do so far. One of them is to further study the effects of mergers and feedback in black hole growth in dwarf galaxies. Another one is to go to higher redshifts and try to detect seed black holes at redshifts as high as possible, even at birth. In the case of going to higher redshifts, as I said before, for the Cosmos survey searches for AGN using the VLA, we found a source at a redshift of 3.4. This was the record holder for an AGN in a dwarf galaxy, but this was a photometric redshift. Very recently, we are working on one of the sources found in this work of radio AGN, in which we have a spectroscopic redshift at 1.9. And also, we are also looking for AGN dwarf galaxy at high redshifts using the Viper survey. Here we have a sample of more than 1,000 broadline AGN, for which we are fitting the spectral energy distribution from the optical to the UV, X-rays, and even radio regimes, because in the Viper survey, we also have a multi-wavelength coverage. As you can see, we have stellar masses. We apply a cut at 9.5 to ensure we have dwarf galaxies or low mass galaxies. And by doing that, we find 22 sources with several broad emission lines, not only at low redshift of H alpha, but up to redshift of 2 using carbon 4. Okay, so this is a very nice sample of broadline AGN dwarf galaxies at high redshifts. The other option is to go to high redshifts using the next generation of observatories. We expect James Webb to be able actually to discern between direct collapse black holes and population 3 stars by means of the SED photometry. In the future, also Athena and the LINX X-ray mission should be able to directly detect direct collapse black holes of in between 10 to the 4 to 10 to the 6 solar masses at redshift 10. And this is one very nice example of a direct collapse black hole candidate at a redshift of 6.6. This is called CR7 from Cosmos redshift 7. The source is a strong Lyman alpha emitter, for which a black hole mass and an X-ray luminosity are estimated around 10 to the 6 and 10 to the 43 X per second, respectively. And for the source, what we did in order to infer whether it's a direct collapse black hole or not is to apply the fundamental plane of black hole accretion to estimate its radio flux. So we have the black hole mass, the X-ray luminosity, applying different fundamental planes, which are these different colors that I'm showing here, these different colored lines. We find different estimated radio fluxes for CR7, which I'm plotting here. This is flux versus frequency. And these black regions here, black lines, these are predicted sensitivities for different future surveys, such as the next generation BLA or the SKA final survey. And we see here with this dashed line, this is the expected flux from an H2 region at highest redshifts. We see that for frequencies below 3 gigahertz, we should be able to distinguish between a direct collapse black hole and an H2 region with the SKA final survey. Okay, so the SKA final survey should tell us whether a source such as CR7 is a direct collapse black hole or not. But we can go beyond that and estimate which is the direct collapse black hole mass that would be required so that such black hole can be detected with the SKA final survey. And I'm plotting this here. It was computed again using different fundamental plane correlations. This is now redshift, and this is the direct collapse black hole mass at 500 megahertz. Now we see that with the SKA final survey, we could detect direct collapse black holes of nearly 10 to the 6 solar masses by redshift 8. And if we go to higher redshifts, at redshift 20, we should be able to detect direct collapse black holes of in between 10 to the 6 to 10 to the 7 solar masses. So direct collapse black holes at birth should be able to be detected with the SKA final surveys, therefore proving the formation pathways of the first quasars in the early universe. And of course, another way to detect intermediate mass black holes is via gravitational waves. There has been actually already one case of a 140 intermediate mass black hole coming from the merger of two lower mass stellar mass black holes. Now, with current interferometers, intermediate mass black hole binaries of in between 100 to 10 to the 3 solar masses should be already detectable. But if we want to go to higher intermediate mass black hole masses, we should wait for LISA. And LISA, in synergy with the SKA and the LINX X-ray Observatory, will be able to prove intermediate mass black holes through accretion and mergers at similar mass redshift ranges, as you can see here, of in between 10 to the 5, 10 to the 6, while the lower ones of between 100 and 10 to the 3 are missed by LISA and are able to be detected, can be detected by current interferometers. So I've shown you that the seeds of the first supermassive black holes are required, the seed intermediate black holes are required in order to explain the first supermassive black holes formed in the early universe that we detect as quasars by redshift 6 to 7. These seed intermediate mass black holes could be found as relic intermediate mass black holes in the local universe, in globular clusters, for which accretion signatures might be detectable in the future with the SKA, or the next generation BLA. Also, as wandering intermediate mass black holes in the Milky Way, and we expect tens of such intermediate mass black holes with a bound stellar cluster to be located in the halo of the Milky Way. And such relic intermediate mass black holes could be also found in galaxies and as AGN in dwarf galaxies, detectable so far up to redshift 3 with deep and large surveys, for which we have been finding that the decrease of the AGN fraction with a stellar mass suggests that direct collapse black holes should be the predominant source of formation of seed black holes. However, we note that mergers and AGN feedback are becoming very significant. This might yield significant growth of the seed intermediate mass black hole. So further studies have to take place in order to assess the role of AGN feedback in dwarf galaxies, and also to characterize the impact of mergers on growing intermediate mass black holes in dwarf galaxies. And as I said, the next generation of observatories are the ones that will be able to directly detect seed intermediate mass black holes at birth. So the future is promising, and stay tuned. Thank you very much.
Great, let's thank Mar for that excellent talk. Really exciting results and very nice summary of past work and future prospects in this field. So there are a lot of experts in the audience who, who've pushed the limit on dynamical black hole masses in the low mass regime, nuclear star clusters, mid-infrared variability for finding dwarf galaxies, corona lines for finding dwarf galaxies, and X-ray observations. So we have a very exciting audience here. So questions for Mar? So Timos?
Yes, you mentioned that some of the ULXs are neutron stars because we've seen the oscillations, and the brightest ones are intermediate mass black holes likely. Could you show us the spectra of those that are known to be neutron stars and those that are not? So that should be obvious in an accreting neutron star from intermediate mass black hole. In the X-ray spectrum alone, that should be sufficient to tell the difference.
Yeah, actually, for the ones which are neutron stars, they have very nice X-ray spectrum, and have features that indicate the presence of superinton accretion on neutron stars. For the sources I've showed here, for HLX1, which is a very bright source, there's also a very nice X-ray spectrum, but not for the other two, which are not so bright. Actually, for the one I showed, maybe I can go back to the slides.
Well, is there a reference I could look those up?
I can look for it and send you an email if you want. Now I don't know.
Okay, fine. I don't want to take it. Somebody else has to ask a question too. Thank you.
Yeah.
Thanks, Timos. Christina?
Hi, Mar. That was a really fantastic talk. Thank you so much. I had a question about the predictions for future radio telescopes and surveys. I don't know if it's easier to go back to the slide that had the comparison between SKA and NGVLA, but I was just kind of wondering if you could explain a little bit more why the low frequency regime is more better suited for detecting the direct collapse ones. Is there like an assumption on the spectral shape? Would you get anything else from high angular resolution, like with NGVLA?
Yeah, well, basically we apply the fundamental plane at 5 gigahertz because it's how it's usually taken at 5 gigahertz. And then we have to move it with redshift to these low frequencies of 500 megahertz. It's because of applying the fundamental plane at 5 gigahertz and going to rest frame. And yeah, the sensitivities, we took them from different published works already. Of course, I guess the sensitivities might change as they work on these surveys, but these are the predictions we could make so far, at least for this below 3 gigahertz here we can distinguish with the SKA final survey, not so much with the next generation BLA, you can see it here. And then in the second work, the predictions, we do them with the SKA final survey because we saw it has more sensitivity than the next generation BLA. But this can change with time, as I said, because I guess, well, you know better than me, right? I guess the sensitivities might not be the final ones.
Yeah, I guess so. I was more wondering like what kind of assumption was folded into like the spectral shape. Like what if they are predominantly peaked spectrum sources, peaking like in the rest of the gigahertz regime? I guess, you know, when you put high enough redshift. Yeah, I guess I was wondering.
Yeah, sorry, I missed that. This was assuming that the typical radio spectral index, I think it was of 0.7. Now I don't remember exactly. It was, so we convert assuming a typical spectral index for active black holes, radio black holes. Yeah.
Okay,
to convert from one frequency to other. Yes.
Great, thanks, Christina. Karen?
Hi, Mar. This is excellent talk. Thank you. And thank you for organizers to have it open for people from the community to join in. I'm at Vanderbilt and I'm part of the LIGO IMBH group. So thank you for the nod for all the IMBH efforts. Detectors, let's say LISA and the other ones that we get to see this 10,000 solar mass or so IMBHs. Do you have an expectation on would it be more equal mass mergers like how we end up seeing currently in LIGO, or would it be more of this, intermediate mass ratio of 1,000 solar mass black hole with maybe a 10 solar mass black hole of that kind? Is there a sort of a expectation of one side to the other in mass ratios of mergers?
Yeah, there are many predictions, and well, actually, something like this was not predicted at all, right? Because this is supposed to be in this Penn stability gap. So this tells you that maybe predictions are not so predictable. And actually, just last week, I was in Zurich working with a group of Lucio Meyer. And actually, what we are doing now is trying to prove whether such intermediate mass black holes do actually merge, because it's not so easy for them to shrink and form a binary and finally merge. So although there are many predictions about the number of detections that we will find with LISA and so, we first should really know whether they will merge. And this is something we are currently working on with this group, working on simulations to see if, when you have the merger of two dwarf galaxies, and in each dwarf galaxy you have an intermediate mass black hole, whether the intermediate mass black holes do actually sync and merge, or whether they stall. So I would say that any predictions we have right now are not definitive. There's still a lot going on, and yeah, we'll see what happens. So I cannot make any certain prediction, let's say.
Well, thank you so much.
Thank you.
Thank you. Anil, and then Stephanie.
Yeah, thanks for the talk. I wanted to ask about the radio jets that you were showing earlier. And when you see like a source where you have an X-ray source and you have a radio, like two lobes on either side of it, I had kind of two questions. One was, is just the morphology by itself convincing to you? I mean, I don't know enough about how common, like this to me seems pretty, it's quite remarkable that there's these two lobes right around the source. And then the second part is for the fundamental plane work, do you just take the core emission and ignore the jets, or how does that work?
Yeah, so first of all, Anil, sorry that maybe I didn't cite here all these works also about variability, as you were saying. Savita works also on direct measurements of black hole masses. I didn't have time to show everything, so I focused more on active black holes, let's say. And secondly, yeah, sources like this, this looks very nice. Actually, I was so excited when I found this with the BLA. However, only from the morphology, you cannot say this is an intermediate mass black hole. Because this, as I say here, actually, I didn't mention it, it could also be a very big radio nebula. So it could be also nebular emission. That's why we went for BLBI, radio observations. Because this way, if you have core emission, you can apply this fundamental plane. Having these extended radio jets, you cannot apply the fundamental plane. And this is the only way we have to estimate the black hole mass, because for these sources, we don't have any optical spectrum. There are no broad lines. There are no dynamical black hole mass measurements. So the only way to estimate whether this could be an intermediate mass black hole or not is via this compact radio emission here and the fundamental plane, or the X-ray spectrum, as someone else was saying. But this source is not so bright. And the problem is that, well, this is Chandra with XMM, which is when we would have a very nice spectrum. The source is not resolved. You cannot see here, but there are actually 3 sources next to each other, which are not resolved by XMM. So for instance, for this source, we cannot have an X-ray spectrum from which also estimate the black hole mass, which could be another method.
I guess I'm just wondering then, with the high redshift stuff, like if you have this emission here, which I think looks like it's dominated maybe by the jets, and then you move this to high redshift, all that's going to be unresolved, right? And so it seems like then that really complicates the use of any kind of fundamental plane stuff at high redshift, right? I mean, does that is that a is that typical?
So for the high redshift, for the high redshift, we don't apply the fundamental plane. The black hole masses we estimate are either from correlations for black hole mass with host galaxy. For instance, from the stellar mass, we estimate the black hole mass, or from broad lines if we have broad lines. We have not applied the fundamental plane to these high redshift sources.
Okay.
Yeah. Thank you for noting that.
Thanks. Yeah.
Thanks, Anil. Stephanie?
Yeah, hi Mar.
Hi.
Really like your talk. And I have maybe 2 questions. One is a bit more specific. Could you go back? You had a slide, I think it was a manga result where the AGN was seen off center, and then you had a broad H alpha for a black hole mass.
Yeah. Well,
Yeah.
Either this one
I think the one after.
or this one. Yeah.
Yeah, this one. Okay. So to me, it's quite convincing that it could be indeed the AGN emission, and maybe it's blended in the center with star formation, or maybe it's switched off, recently or something like this. So I'm trying to understand here, the broad emission, is it coming from the far away region and not from the center? And I'm trying to understand with the accretion disk, how,
this is something I was also puzzled, because actually here, this spectrum I'm showing here is the stack of the AGN spaxels.
Okay, so the red ones, yeah.
Exactly, only of the red ones. And there's broad emission.
Yeah, I wonder if there could be any reflection or something, maybe. That's very intriguing, yeah.
Yeah, so it's broad emission from these spaxels here,
Yeah, because they're not in the center. Yeah, that's why I was just like, wait a minute.
Yeah.
Okay, that's very interesting. And my other question is more general. So I started to think when you were presenting your results, because a few times you were mentioning the role of minor mergers. So from your impression, does it seem like a minor merger is susceptible to both trigger AGN in the massive central and in the small satellite? I don't know, I imagine there's already simulations of this kind of stuff, but are you mostly interested in just figuring out what minor mergers do to the satellites themselves?
Yeah, so I know there are simulations on that, whether there's AGN triggering in minor mergers. Now I don't remember, because I've read so many papers, but I know this can happen. So, well, of course, you can have several results depending on which simulations, but I've read that, yes, there can be triggering also in minor mergers of the AGN in the minor galaxy, in the dwarf galaxy. Yes, maybe I can look for the references and also say.
Yeah, I mean, we can talk later, but thank you so much.
Thanks, Stephanie. Renuka?
Yeah, hi Mar, that was a really great talk. I just had one question. So you had some of these wandering black holes from the manga survey, right? Around 29 that you were saying. Have those been looked deeper into it, the IMBHs in those?
So from the manga survey, what we have is this of nuclear AGN that I'm having here.
Yeah.
Okay, so these are not wandering. Well, okay, yeah, these are wandering because are of nuclear. Yes, indeed. So yeah, I was more thinking of the Milky Way ones. No, okay. So yeah, we call these of nuclear. But yeah, it's the same. So we are actually doing the same work now, but for the latest release of the manga survey, which includes way more galaxies. Yeah, and we should have the results pretty soon. But yeah, we expect.
Okay, but have these been like individually looked into, or
what do you,
I mean, like more in detail? I don't know.
Okay,
like from
yeah,
other
well, we
surveys.
applied, yeah, we got BLA observations for a few of these sources. Yes,
Okay.
we have a student also working into that. And we might apply for Chandra observations because, well, the problem is that, you know, it might be that the AGN is here, but is obscured, right? So that's why you don't see it in the optical. So to really discern between an off-nuclear AGN or just obscuration by star formation, you need additional observations rather than optical. And for that, we applied for BLA, and we could also go for Chandra if the obscuration is not very high. Yeah. For now, we have BLA data.
Oh, okay. Thanks.
Yeah, maybe also you should do ground-based near infrared.
I knew you would say that.
But,
yes. Indeed.
And with AO, let's make it extra hard, right, Kathy?
We tried one with AO, yes, but yeah, the sources were very faint.
Yeah.
Work out. No.
Yeah. Any other questions? So it's very late for Mar, and I have a lot of questions, and I won't ask you. I'll do it offline at a nicer hour, because I think is it 8 o'clock there for you? Or
I think it's 7 p.m. It's okay.
7 p.m.
Yes.
So yeah, thank you so much for joining at this late hour and for this wonderful talk. It was really nice summary and very exciting work. So let's thank Mar once again for this wonderful talk.
Thank you so much.